Today I'm going to talk about a new chapter, chapter 6, introducing what we call the truss structures. So far we have learned the most fundamental stuff for this class, which is chapter 4. So basically, we know how to calculate the reactions or how to calculate the cable forces and so on, just based on the equilibrium equations after we identify the rigid body. So any basic rigid bodies, once we identify, we plot the free body diagram, we can come up with either 3 equations for 2-dimensional problem or 6 equations for 3-dimensional problem. So starting from chapter 6, we're going to talk about one of the special rigid bodies, and that is called the truss. And then later on, chapter 7, we're going to introduce another special case of rigid bodies, which is called the beam. So for this chapter 6, we're going to introduce truss structures, and then we're going to learn how to calculate the internal forces, because this is a very important concept for us to do any engineering structural design in the future. Because we do need to know what kind of internal forces, or later on we call the stresses, in the structure, so that we know where we're supposed to put more materials and where we don't have to put more materials. Okay? So this chapter, we're going to talk about analysis of truss structures. So this is the typical truss structure you can frequently see when you are anytime walking by a certain construction of buildings and sometimes bridges and so on, right? Obviously, you can see there's a lot of slender members connecting together to form this kind of structure. Obviously, the reason normally we use this kind of structure composing of a lot of slender members, the most important thing is a cost issue, right? So because we want to save the money. So that's why we don't want to use a lot of materials. So obviously, any kind of engineering structures are kind of taking advantage of slender members. And this one of the slender member combination is called the truss. And obviously, another one is called the beam. Altogether, we call the frame. Okay? So this chapter, we're going to talk about this special case we call truss. And now, I want to introduce 2 concepts in this chapter. Number 1, this is what we call the internal forces, which we never talked about before. And then number 2, we're going to give you some kind of definition about a truss structure. Okay? So these are the 2 major issues we need to talk about first before I will teach how to calculate those internal forces. So first of all, what is called the internal force? In chapter 4, we talk about the reactions. Reactions are kind of external forces acting on the rigid body, because with the reaction we can support that such rigid body with applied load or applied moment on the rigid body, and then we can calculate what's the reaction or with resistance, okay, so that we know the support need to provide that much. On the other hand, even inside the rigid body, specifically for this problem we call the truss, we also need to know how to calculate the internal force. Typically, we don't see internal force. For example, we see this kind of structure. Okay, so we have this kind of frame with a cable here, and then with a weight, and then we may say, well, because of this situation, what is the support, or what is the cable force needed to make sure this rigid body is in equilibrium? That's very easy, because we can basically use the concept we learned from chapter 4 to easily calculate the reaction and also the cable force by first plotting a free body diagram based on the rigid body. For example, we see this the rigid body like this. Okay, we put them all together, and then we have this kind of crate. So then we cut here. That is to isolate the connection from outside about this rigid body, and then correspondingly we give a force. Okay, so this is the force due to this self weight. That's easy. And this is the pin support. If this is a pin support, when we cut this one to isolate the rigid body from outside world, then obviously we need to give 2 reactions. For example, we call AX and AY. And then finally, we see there's a cable connecting between one point in the rigid body D and also another point with a support, with a ground. So then obviously we need to cut somewhere here or anywhere, and then correspondingly we gave this cable force. So this is what we call the free body diagram we introduced in chapter 4. And very easily we can calculate those forces, because for this typical two-dimensional problem, we have three equations, right? By collecting all the forces in x direction, that's the first equation. By collecting all the forces in y direction, that's equal to 0. That's the second equation. And then we can take a moment equation. For example, we're going to take a moment of all forces about this point, and then set equal to 0. That's the third equation. So we can basically solve these three unknowns, ax, ay, and the t. So those are something we just talked about in chapter 4. Okay? Now, the other question is, inside this 3D body, for example, it's somewhere between B and E, or somewhere between C and B, or C and D, or C and E. Are there some kind of internal forces? Are there something connecting? The answer, of course, is yes. But we just cannot calculate unless we make the further cut. And these are the forces inside the 3D body, which is what we call the internal forces. So in order to calculate internal forces, we have to make the further cut. For example, if we want to cut somewhere between B and E, and then we cut somewhere also towards E direction, but close to E, then we're going to separate this part of the 3D body, which is a slender member, from the rest of the 3D body. So if that's the case, obviously, when we cut this point, point B, the point B is connecting between this slender member and this slender member. So then we're going to give a force acting on point B. And this is one of the internal forces we can call due to this member on this part of the 3D body. And we call, for example, this FB. Similarly, when we cut this one at point E, then there is another internal force after we make the cut going to applying on point E due to another part of the 3D body member. And that's another force. And then based on this new free body diagram, then we can calculate those internal forces. Similarly, if you want to calculate the internal force at point C or at point E, then what you need to do is to plot this part of this 3D body, CEF, for example. At point F, there's still another force given due to the crate. At point E, because we cut here, then this time there's a force acting on point E on this part due to this part of 3D body. And these two forces are always with the same magnitude but in opposite direction because of Newton's third law, the action and the reaction. So similarly, when you cut here, you may give another force due to this part of the 3D body on the point C. So either you can split into two components or just give one force in any direction which we have to calculate. And then altogether, this one form another free body diagram. And based on this new free body diagram, obviously we can also set up three equations. Okay, so this is the typical way for us to calculate internal forces. The bottom line is, from previous free body diagram we learned in chapter 4, we cannot calculate the internal forces. In order for us to calculate internal forces, we have to make the further cut by appropriately considering part of the 3D body. And that's the job we need to do in this chapter. So first of all, let me introduce a truss structure. So if we see a certain structure, something like this, composing all the slender members together, this is the first requirement to be a truss structure. So if you look at the truss structure, all the members forming the whole structure must be slender members. Okay? Number one, this is number one. Number two, all these slender members are connecting at a certain point, which we call joint, either due to welding or due to bolting. Okay? So, for example, at point C, this is a bolted connecting all the three slender members together with certain bolting technology, or sometimes we can weld. So either way, I think we have this. Yes, either bolted or welded connections are assumed. It have to be like this in order to call the truss, which means they are internally pinned together. In other words, at this point, the rotation is okay, but it's not allowed to move from this member to other members. And the forces acting on at all members' ends reduce to a single force and no couple. So in other words, number one, all the slender members are connecting through either bolting or welding. And then number two, all the forces must be applied only at those joints. So with these three conditions, we can call this structure is a truss. So first of all, in order to make a truss structure, all the members must be slender members. Number two, they all connected through through joints, which are either bolted or welded. Number three, which is the most important one, you have to check all the applied forces must be acting on those joints only. In other words, if I change this force applying on point D to be somewhere here, for example, because in fact I can apply a force at this point. If this is the situation, then the whole structure is not called a truss. Even though the structure is still identical, which we had before, if this force moved from point D to somewhere in between, then the whole thing is not called a truss. In other words, we cannot use the principles we're going to learn in this chapter to calculate any internal forces if there is one or multiple forces acting in between instead of at each end. The reason we have the third requirement is simply because if we have all the applied forces acting on those joints only, then each member, in fact, form what we call the two-force body, as we originally introduced in chapter 4. So if you look at any one of these slender members, then all the forces applying on those slender members are at only 2 points. There's no third point somewhere in between. There's no additional forces acting in between this one, so that each slender member, you have this, or this, there are only 2 forces acting on 2 locations. And if that's the case, this rigid body is called a two-force body. And based on the conclusion we have in chapter 4, for any two-force body, the conclusions are, number one, these 2 forces must be having the same magnitude, number one. Number two, they must apply in this direction, connecting these 2 points. And number three, these 2 forces are in opposite direction. So either way, these forces are something like this, which is opposite, or something like this, which in compression, to have the slender force in slender member in compression. And that's the definition of a truss structure. So for example, if we see this kind of a pedestrian bridge, just in case, okay, so although it's 3-dimensional, which we're not going to talk about, if there are forces acting in between the slender member. You see, this is a slender member, right? Or this is a slender member. If there are any forces acting in between, then this is not called a truss. However, if we're looking at this vertical part of the rigid body, this one, it can be a truss if all the forces are applying on those joints only. And typically for these kind of bridge, when we design, we want to make sure all the forces are applied on those joints only. In other words, if we are ignoring all the self-weight, then any additional force acting on this side, on the other side, can be applied on those joints only. And then this part, again, is still a truss member. And the other way from the other side, that's also a truss member. But this one, on the bottom, something like a deck, it cannot called a truss. It's simply because you have the forces acting in between the slender members. Okay? So the members of a truss are slender members, number one, that's the first requirement, and are not capable of supporting large lateral loads. In other words, if you do have the lateral somewhere in between, then it's not called a truss. And the loads must be applied at the joints only. And that's the third requirement for being a truss structure. So let's say we can find out some truss structures satisfying all the requirements. Then the next question becomes, how are we going to calculate the reactions? How are we going to calculate the internal forces? So in this chapter, we're introducing 2 methods. The first one is called the method of joints, followed by another method we call the method of sections. Okay, so today I'm going to talk about the first one, which is called the method of joints. So we call the method of joints. Well, let me just show you another slide to show you there's a lot of different kind of trusses, but they are always following the 3 requirements. If you look at this one, they have a different name. For example, it's called the Pratt structure truss, and all these different kind of bridge models. They're all forming a truss structure. Typically, you can see if you check all these kind of examples, they are always having slender members connected to each other, and at all the connecting point, they are either using bolt or welding to form together. And number 3, if there are any loads, they have to be applied at those joints only. Okay, there are a lot of different names which I even cannot remember, but the most important thing is if we gave you a certain truss structure, we need to know how to calculate the member forces or the internal forces inside each slender member. Okay, so today we're going to talk about the first method. It's called the method of joints. In other words, if we introduce a method of joints, then we need to look at each joint and then to establish the equilibrium condition or equilibrium equations based on Newton's law. So let's take a look about the original structure like this. Okay, so once we have this is the same structure as we just had here, right? So if this is the truss structure having 5 slender members connecting each other, supported by a pin at point A and also a roller or rocker, you can call this a rocker at point B. In addition, there is a force acting on point D. So first of all, we do need to calculate the reactions as a first step. And that's very easy to do that because we just identify the whole truss as a rigid body. And then at the point A is a pin end, then we gave 2 reactions. At point B is a rocker, we call the roller, you give another reaction, and then all together form the free body diagram. And that is something like this, right? So we have the rigid body here, there's applied force acting on point D. At point B is a rocker, that's why we gave a reaction called RB, which is unknown. And then at point A is a pin support, that's why we have the reaction RAX and RAY. So for this free body diagram, there are 3 unknowns, RAX, RAY, and RB. This is a typical 2-dimensional rigid body problem. With the 3 unknowns, we can establish 3 equations, right? Collecting all the forces in x direction, that's the first equation. Collecting all the forces in y direction set equal 0, that's the second equation. And then we need to collect a moment equation. For example, we collect the moment of all forces acting at this point is equal 0, that's the third equation. Combining those 3 equations, we can solve for these 3 unknowns. That's typically the first step, allowing us to calculate the reactions first. But after we got those reactions calculated, then we need to look at some joints. And then we're going to cut those slender members connecting to the joint. And then we'll see how we can calculate the internal forces. For example, if we look at point C, assuming we got these reactions first, if we look at point C are having 3 slender members connecting together. So I'm going to set out the free body diagram at point C only. In other words, I plot point C first, and then I need to cut this slender member AC. When I cut the slender member, there is a force acting on point C due to this slender member. So that I can call this force. It's called FAC, for example. And then there's another slender member CD. When I make the cut here, then there's another force acting on point C due to the slender member CD. Then I give another force. And then furthermore, there is another force acting on point C due to this slender member CB. After you make the cut, then you give another force. So from the free body diagram about this point only, there are 3 forces acting on point C. At each point, we can establish 2 equations. You may say, why not 3? Well, when we talk about the free body diagram for each point or each particle, there are only 2 equations. The third equation, which is a moment equation, doesn't work. It becomes a trivial equation because there's no distance involved. You only talk about 1 point. That's a chapter 2 stuff. So in chapter 2, when we plot the free body diagram about each point, typically we have 2 equations only. In other words, we can collect all the forces in x direction, set equal 0. We collect all the forces in y direction and set equal 0. So having 2 equations at each point, we can calculate up to 2 unknowns. So in other words, at point C, this time we have 3 unknowns, right? Because these are the 3 internal forces due to the slender members acting at point C. If there are 3 unknown internal forces, there's no way actually we can calculate these 3 forces because we only have 2 equations. So on the other hand, we have many other locations which are forming what we call the joints or the welding point. And for example, at point A, if we are looking at point A, and then we're going to plot the free body diagram at point A only, then what we're going to do is, at point A, we cut it between A and C, then there is a force acting on point A due to this slender member. And the AD is connecting at point A. When we cut AD, there's another force acting at point A due to the slender member AD. In addition, this point A is supported by a pin with RAX, RAY. But RAX, RAY were calculated before. So in other words, this time we already know RAX and RAY. So then, from the free body diagram at this point A, how many unknowns right now acting at point A? There's only two unknowns, this one and this one, because these two were calculated in the previous step. So in other words, from this free body diagram at point A, we can collect all the forces in x direction equal to 0. We can collect all the forces in y direction set equal to 0. Then we can calculate these two unknowns. So in other words, if we are picking point A and to establish the free body diagram equations, it is doable. If you are first picking point C, it's not a good idea because you have three unknowns. There's no way you can solve for these three unknowns by using two equations. Obviously, you can select point D. At point D, there are three unknowns acting at point D due to these slender members. So typically, we cannot calculate those three unknowns, although the force is acting here directly, which is a given force. You can also look at this point. At this point, if we plot the free body diagram at point B, then it is quite doable because at point B, first of all, there is a reaction due to the rocker, which we have calculated already from previous step. So in other words, this RB is given force now. We need to cut between B and D, then we gave another force. This is the unknown force due to the member BD. And we need to cut between B and C, and then we add another force acting on point B due to this slender member. From this free body diagram, there are only two unknowns, this one and this one, because RB was calculated before. So from this one, we can also calculate these two internal forces. So the fundamental issue is we need to be a little bit careful when we select the joints. If we are randomly select some joint with more members connecting to this point, it doesn't help us calculate all the unknowns. But if we are selecting some point like point A or point B, there's only two members connected, then most likely we can calculate the member forces. Okay? Of course, later I will give you a few examples just to demonstrate how we're going to calculate those member forces. But in general, this method is called the method of joint, by looking at the joints only and establish the two equations. Someone have a question? Yes?
So when you kind of disable each member, when you have from A to C, the forces are going into it, but from C to D, they're going out. And then from A to D, they're going out.
Right.
The other ones are going in. How do you distinguish whether the forces?
It is really up to us to make assumption first. The reason we have to make assumption is simply because now we do not know the internal forces is in compression or is in tension. We do not know it. So it's really up to us to make a first assumption. So for example, at point C, you see here, I make the cut here and then I gave a force acting on joint C into that point, right? So you may argue with me by saying, why do I have to assume like this way? Can I assume a force leaving that joint C? It definitely is not a problem. And in fact, I'm going to give you certain kind of suggestions when we are making the cut, and because we do not know the force in tension or in compression, then in general, I'm going to assume all the forces are in tension first. And then if the force is in tension, then all the forces acting on the certain joint is always the force leaving that joint. And that's assumption, by the way. It doesn't mean it's guaranteed to be in tension. After you calculate those forces, if those forces calculation gave you the positive number, then in reality, that's the result is consistent with what you assume. But it can be with a negative direction. If that's the case, in fact, your assumption is wrong. But your assumption is perfectly wrong. In other words, you don't have to recalculate. You just simply change the direction. Okay, so when I give you the example, I'll show you how we're going to make the assumption. But on the other hand, that's the assumption I normally make. It doesn't mean everybody have to follow. You can use your own assumption. That's not a problem. The bottom line is, once you make assumption, you need to memorize that assumption. Okay, so either you assume it's in tension or assume in compression first, it doesn't matter. After you calculate, you can correct your assumption. Okay, any other questions? Okay, there are some special cases. For example, we have 4 members connected, 2 of them in one direction, 2 of them are in other direction. And the conclusion is these 2 forces must be equal with other. These 2 forces must be equal with other. Okay? Similarly, you have 3 members connected with another additional force acting at point A. These 2 form a certain direction. These 2 force members forming a certain direction. We got the same conclusion. I will come back to talk about these special cases. The most important or commonly used cases are this one and this one. In other words, if we have 2 members connected at point A and they are in different directions, in other words, this angle is any angle rather than 180 degrees, then both members, in fact, are having 0 member forces. Later I will come back to show you why it is this case. Similarly, when you have 3 members connected to a point A, 3 members connected to point A, 2 of them are in one line and the third one is the third line, then the third member must have the 0 force member inside. And these are the 2 most commonly used cases. I will come back to talk about this one after I finish this example.